All right, so let's look at another hexagonally based material, and this is hexagonal close packed again, but this is corundum. So corundum is known as the chemical name for Al2O3, aluminum oxide, but it can also form in other compounds with similar stoichiometry. So iron oxide Fe2O3 and vanadium oxide V2O3 as well. So that's the kind of stoichiometry we tend to see. And this is a more complex structure. As you can see, it's a bigger unit cell. It has more atoms. But the basics of it are the same. We have hexagonal close packing of the anions, which is oxygen in this case. And then we fill in the interstitial sites. In this case, 2/3 of the octahedral sites get filled, which is why the unit cell becomes bigger, because we need to essentially look at 2/3. And so it's a more complex structure. If we look at the coordination numbers for aluminum, which is in the blue, so aluminum's the smaller, red is the oxygen, which is bigger. The coordination of the aluminum is 6. So if you can kind of look at some of these, hopefully you can kind of see that there's 6 oxygens around an aluminum. And then the oxygens, which are the red, are coordinated by 4. And so again, you hopefully maybe you can pick one out and find that it's surrounded by 4. If it's on the edge, keep in mind that it may be coordinated by things in the next unit cell. So the coordination numbers are 6 and 4. It does have that HCP stacking of the anions, so AB, AB. Again, 2/3 of the octahedral sites are filled. And an important thing to kind of note here is that the octahedron, so it's, and here you can see the shapes. So each octahedron in the z-axis shares a face with another octahedron. So again, this is the type of sharing that we said was least favorable, because it brings these aluminums, in this case, really close together. So the way this structure gets around that is, if you notice, so there's 2 octahedrons, but then there's an empty site above and below. So let's look at these 2 octahedrons. So above here and below here, there's empty spaces. There's not a polyhedra. So what that does is that the aluminums in these sites can actually spread out a little bit, right? Because there's nothing on this side and this side. So it kind of distorts itself a little bit in order to keep the cations away from each other. So that's kind of one way that we can still have this face sharing along that direction. But otherwise, you can also see other forms of sharing as well. So we actually have the vertex sharing here, and then we actually have some edge. So there's a range of different sharing that we see here. So this is a rather complex structures in this case. And again, like I said, this is Al2O3's structure that we see. All right, so let's look at an example using the Pauline's rules we talked about in previous modules, and using the table in our book, so table 3.3. Let's see if we can predict the structure of lithium sulfide. So using the information, and I've given it all to you here. So you've got the ion sizes, you've got the radius ratio table here, and then you've got the table from the book. So see if you can use those Pauline's rules that we talked about for lithium sulfide and predict what the structure will be for lithium sulfide, given that's an ionic material. So do that, and then we'll come back and take a look at that. All right, so let's calculate or predict the structure for lithium sulfide. So the stoichiometry wasn't drawn out, But if you go back and look at the table in those slides, you'll see that lithium is +1. So this is always lithium +1. And then sulfur can form into sulfide, which is 2-. And then to balance that, we need 2 to 1. So we get lithium 2 sulfide. So that's how I arrived at that. So this also gives us the charges, right? So the first thing I want to do, though, is get the radius ratio. I want to get that. So I'm going to look for the cation. So back on the chart, the value for lithium plus was 76, and this was in picometers. So as long as we're consistent, it doesn't matter. And then same going back into the chart for sulfide, it's 184 picometers. So if we take that division, we get 0.413, and using the table for the critical values, we see that puts it squarely in the, or barely, I should say, in the coordination equals 4. So it's really close, as you can see, because 0.414 is the upper bound for the next. So keep in mind that this is very close. So that gives us a coordination, and this is for the cation. So we got the cation coordination of 4. And then we can use our bond strength equation, right? And we know the charge of the cation is +1, and the coordination is 4 from here. And so this is just 1/4, right? And then if we use our similar equation, right, solve for, and again, this was the negative of this, and so coordination, just rearranging, and then we know the charge of the anion, -2 over minus the bond strength, which was 1/4. And so the charges are going to cancel out because, it's a coordination, so it shouldn't be negative. And so that gives us 8. So our anion coordination is 8. So I'm going to write it out like you might see in that table now. And so I have the coordination of the cation is 4 relative to the 8 for the anion, and my stoichiometry is M2x. So let's go ahead and I'll grab the book real quick, and let's take a look at the types of structures that can form into that coordination and that stoichiometry. Bear with me for a second as I find it. Okay, here we go. So this is the table from the book, table 3.3. So obviously it might be a little blurry here, so feel free to look it up yourself so you can see. But we're looking for, again, this kind of table is helpful because it gives us the coordination numbers and it gives us the stoichiometry. So whichever way you want to approach it, either look for 4.8 or the M2x. I'm going to look for M2x because that's the more unlikely. And so first one I get actually is 4.8 M2x, and there really isn't any others, so to speak. So it's really the only M2x form that we have here, and that is anti-fluorite, right? So based on this table here, we expect that this is going to be the anti-fluorite structure, and you'll see a lot of similar types of compounds along with one lithium compound here. So that's what we predict based on the table and the Pauline's rules for this. So we expect anti-fluorite based on these calculations. I will caution you though, a lot of these, if you go through various compounds, covalency matters, right? So that can affect the results, and so you might not always get what you expect. And also looking at the values for cations and anions, you're going to find that the radiuses change with respect to the coordination number itself. And so getting values for the cations and anions is actually tricky in that you already are supposed to know the coordination numbers. So it's a bit cyclical. And so we'll only do a few examples here, but you want to keep those things in mind. So oftentimes you have to take a guess at the coordinations for these and then work through it and come back. So that's the example here for lithium sulfide.